Everything around us is matter. You and I, we're all matter. In fact, the entire universe is matter. A couple hundred years ago, it was believed that the smallest building block of matter is called an atom. But then, people like Michael Faraday, J.J. Thomson, Rutherford proved them wrong and told the entire world that things like electrons, protons and neutrons exist, which are much smaller than the entire atom. So what we're going to do today is actually focus on the structure of atom, how those protons, neutrons and electrons are actually distributed among the matter, among all the atoms. So, what Michael Faraday did was, he took a glass tube. In the glass tube, he took a negative terminal and a positive terminal. He took a battery with a very high voltage. He took a vacuum pump to take out most of the gas to create a very low pressure inside. And he had a fluorescent coating on the back side of the anode, right? So when he actually supplied the very high voltage, he noticed that some rays were going from the cathode, which is a negatively charged terminal, to the anode, which is a positively charged terminal. And the fluorescent coating was a proof, because whenever something strikes a fluorescent coating, it shines. So because of the shining of the fluorescent coating, we knew that something was moving from the cathode to the anode. When Michael Faraday passed those rays through electric and magnetic fields, he noticed that they are getting deflected the exact same way a negatively charged particle should. And that's how Michael Faraday discovered the electron. The proton, which is a positively charged subatomic particle, was discovered when particles were moving from the positively charged terminal to the negatively charged terminal, which means from the anode to the cathode. That's how we discovered the proton, and those rays were called the canal rays. Now, we know a couple of things due to the Millikan's oil drop disk experiment, which you can find in the link in the description. The electron charge is minus 1.6 into 10 to the power minus 19 coulomb. Coulomb is actually the SI unit of charge. The proton charge is plus 1.6 into 10 to the power minus 19 coulomb. The mass of an electron is 9.1 into 10 to the power minus 31 kilograms, and the mass of a proton is 1.67 into 10 to the power minus 27 kilogram. Now when we look at all these figures, we realize how small a proton is and how small an electron is, or how negligible the charge on it really is. All these values are really important and you have to remember them. Now that we knew that protons and electrons existed, we needed to know how it's distributed inside the atom. So J.J. Thomson, a very famous physicist of his time, said that imagine a watermelon. The red part is the protons and the black seeds are the electrons. Because we knew the electrons are much smaller than the protons, everyone thought, and J.J. Thomson was a very famous physicist in his time, so people thought that this is the right model. And this model was called the plum pudding model or the watermelon model. But then Rutherford wanted to test this model. So what he did was, he performed the famous alpha particle gold foil experiment. So an alpha particle is a monster truck if an electron would be a toy car, right? It's that big a difference. So an alpha particle can go through anything without any deflection. But when the alpha particles were projected towards the gold foil, he noticed that they were getting slightly deflected, and 1 out of every 20,000 came back at a perfect 180 degree angle, which should not happen at all because the entire mass of the protons and electrons is completely distributed in the atom. So all of them should go right through. Imagine a thin piece of paper and me throwing a stone at it. It should go right through. But why is that stone getting deflected or coming back at a completely perfect 180 degree angle? This meant that most of the mass is concentrated in the atom at the center, and the electrons are moving around it. Hence, because the mass is a lot over here, when something hits it, it goes back or gets deflected. So this was the famous Rutherford alpha particle scattering experiment, which proved that J.J. Thomson's model of atom was wrong. And eventually, this model was also proved wrong, which led to the Niels Bohr model of atom. Before we go into the Niels Bohr model of atom, we need to understand these symbols. Whenever you see the periodic table, you would see it is filled with symbols and numbers which we don't understand. So all kind of atoms and all kind of elements are represented by symbols. So hydrogen would be represented by H, carbon would be represented by C, nitrogen by N, bromine by Br, sulfur by S, right? Now what are these numbers? Because you have read all of this in class 10th. What are these numbers? So the atomic number is represented by Z. It is equivalent to the number of protons an element has. We distinguish different elements according to the number of protons they have, because one kind of element will only have one particular number of protons. Now we talk about mass number, which is represented by Z. So the mass number of any atom would be the number of protons plus the number of neutrons, and we don't add the number of electrons because the mass of an electron is negligible, right? Now when you see the periodic table, you would see the symbol over here, which is represented by X. So instead of X, you would write the symbol of that element. On the bottom left side, you write the atomic number, right? Atomic number, which is represented by Z. So this is where you would write the atomic number, and here you would write the atomic mass. So hydrogen has 1 proton and 0 neutrons. Hence 1 is written over here, and 1 plus 0, which is 1, is written over here. But hydrogen has isotopes. An isotope would be an element which has the same number of protons but has different masses. And now how is that possible? Hydrogen has 3 isotopes. It has protium, deuterium and tritium. Protium has only 1 neutron, has only 1 proton. Deuterium has 1 proton and 1 neutron, and tritium has 1 proton and 2 neutrons. Hence the masses are 1, 2 and 3, even though it is the same element. So those were isotopes. Isobars is when 2 different elements have the same masses. So carbon and nitrogen, which have the atomic number 6 and 7 because of the protons, have the same masses because carbon has 8 neutrons and nitrogen has 7 neutrons. So their masses become equivalent and they are 14, right? Now this is pretty simple. We write the charge any element has on the top right corner. So you would know sulfur di negative, chlorine negative, 1 negative, etc. Now what kind of questions would they ask in examinations? They ask the most silly questions. So imagine they say bromine 35, 80, right? So what are the number of neutrons in bromine? It's pretty simple. We know that 80 is the sum of number of protons and number of neutrons. So we know that the number of protons is 35, we know that the number of protons plus number of neutrons is 80, then obviously the number of neutrons would be 45, because 35 plus 45 is equal to 80. So this was pretty simple. A little complicated question would be this. The number of protons of an element are 16, the number of neutrons are also 16, and the number of electrons are 18. Assign the symbol. Now first we will see which element has 16 protons. So we know sulfur has 16 protons. So first we will write sulfur, which is represented by S. Then we will see how many neutrons it has. So it has 16 neutrons, so the mass becomes 32. So we write 32 over here. And then we see electrons and protons. So electrons are more than protons, and the charge of an electron is minus and the charge of a proton is plus. Now because there are 2 more electrons than there are protons, so sulfur has a di-negative charge because there are 2 extra electrons. Now imagine an element which has 16 electrons but 18 protons. Then there are 2 more protons than there are electrons, hence the charge will be di-positive. That's all you need to know about this. If you're a little confused, you can just rewind the video. It's a really simple concept. Rutherford's model of atom was wrong because he said that protons and neutrons are in the center and electrons are moving in a fixed path around them. While when 2 charged particles move around each other, then they must emit energy or must have an external force that's keeping them in that path. And if an electron was emitting that much energy, then it would fall inside the atom. It would not be in a fixed path because it would have no more energy left. In fact, I believe it's in 10 to the power minus 8 seconds it would fall inside the protons. Hence, Rutherford model of atom was wrong and a new model was required. And force is equal to kq1 q2 upon r square is the proof that Rutherford model of atom was wrong. Now, before Niels Bohr came up with his model of atom, 2 very important discoveries took place. The first one was an electromagnetic wave not only behaves like a wave but also as a particle. Now, what is an electromagnetic wave? An electromagnetic wave is when an electric wave and a magnetic wave intersect each other at a 90-degree angle. So this is the x and y axis. The blue line represents the magnetic wave, and the red line on the z and x axis represents the electric wave. You would see that on so many points these lines are actually intersecting each other. The waves are intersecting each other, and this is happening at a perfect 90-degree angle. Hence this wave is an electromagnetic wave. Now, C is equal to nu lambda is a very important formula which is used in almost every question. Now what does this formula say? It says that the speed of light is equivalent to the frequency multiplied by the amplitude, right? Now what is frequency and amplitude? This is the y-axis and this is the x-axis. The wave is moving along the x-axis, okay? This is the crest of a wave and the bottom part is called the trough of a wave. From this point till this point, from the crest and the trough, when the trough ends, the wave ends, right? This entire length is called the wavelength. And the maximum height of the wave is called amplitude, which is denoted by A. Now draw an imaginary line. The number of waves, which cross this line, this imaginary line in 1 second, that would be the frequency of the wave. Now imagine 10 such waves crossing this line in 1 second. We would say that the frequency is 10. Imagine 10,000 waves are crossing this line in 1 second, then we would say the frequency is 10,000. And the SI unit of frequency is Hertz. Hz is how we represent it. Now one more important thing, wave number is just 1 upon lambda. Wave number does not mean anything, it's just a symbol. It's just equivalent to 1 upon lambda, and lambda is the wavelength, which is the maximum length of the wave. I believe you understand this much. This is the previous knowledge of class 10th. Now, what do they ask in examinations? They would give you a very simple question. The frequency is 1368 kilohertz. That means 1368000 hertz. The wavelength is what you have to find. Now we know a simple formula, C is equal to nu lambda. So lambda, which is the wavelength, is equal to C upon nu. Simple cross multiplication. Now C is the speed of light, and speed of light is always constant. Even in air, even in vacuum, even in water, it is almost equivalent to 3 into 10 to the power 8 meters per second. You must remember this. So all we have to do is substitute the values. So instead of C, we'd keep 3 into 10 to the power 8 meters per second. Instead of frequency, we just keep 1368 into 10 to the power 3 second inverse, and which hertz is actually second to the power minus 1. So when we solve this, we'd get 219.3 meters, which is 2 into 10 to the power 2 meters. That's it. That's all you have to do. Now, electromagnetic waves have a lot of types. Microwaves are electromagnetic waves, infrareds, long radio waves. In fact, the visible light which you and I can see is also an electromagnetic wave. But the frequency of other sorts of electromagnetic waves, such as radio waves and gamma rays, X-rays, infrared rays, they are so high or so low that we can't see them. And because these are the 7 main colors, Vibgyor, violet, indigo, blue, these fall in the visible region because of the frequency. That's why we can see them. So this is the electromagnetic spectrum, which is just on my left hand side right now. You take an iron rod and you start heating it. You would realize that first it turns red, maybe it turns blue, and then eventually it turns white and then starts melting. Okay, that's what you would usually see when you heat an iron rod. This means that as you supply energy, different frequencies of light is being emitted, which means that energy supplied is directly proportional to frequency, which means there is a proportionality constant. And Max Planck was the first person who found this proportionality constant, hence it is called Planck's constant. Its value is 6.626 into 10 to the power minus 34 joules second. That's all you need to know when we talk about this formula. Now, that iron rod is actually a black body. It is a black body. Why is it a black body? Because it can absorb and release energies and electromagnetic waves of all sorts, right? So you'd see the colors are changing. It's first red, then blue, then white. Maybe different colors were being emitted which we cannot see with our naked eyes. Hence we say it is a black body, or any body which can absorb and release energies of all sorts is a black body. Now, what is a photon and what is a quanta? Now, the energy that was released in form of light was actually a quanta. It is not released continuously. It is released in very small packets. The energy is released in very small packets, and those packets are either called photons or quanta. If the energy is released in form of light, then we call it a quanta, and if it's not released in the form of light, we call it a photon. As simple as that. Okay? Now imagine there is a very dusty sheet over there. The bed sheets you sleep on, there is a very dusty one just over here beside me. And I take a very heavy ball and I throw it at the bed sheet. All the dust particles will completely fill the room, right? All the dust would completely fill the room. And if I take a very light table tennis ball and I throw it at that bed sheet with a very less speed, then maybe no dust particles will leave the bed sheet, because that did not have enough energy as much as the heavy ball. That is the exact same thing that happen when we talk about photons. The energy of a photon or the energy of a quanta is equal to h nu, which we just studied, right? So when we talk about a red light has a frequency of 4.6 into 10 to the power 14 hertz, and a yellow light has a frequency of 5.2 into 10 to the power 14 hertz. Obviously, because yellow light has more frequency, hence it would have more energy. E is equal to h nu. Hence the photon of yellow light would be more energetic than the photon of a red light, right? So when the red light was projected on a potassium metal, no electrons were released. But when a yellow light was projected on a potassium metal, all electrons started coming out. This means that there must be a minimum energy that is required to remove a proton, to remove an electron. And because a minimum energy is required and h is constant, hence a minimum frequency is required, right? We can ignore h because it's a constant. That frequency is denoted by this symbol. This is this O is called a knot, right? Now h nu is equal to h nu naught plus half MeV square. Now the minimum energy is h nu naught, so we write it over here, and the energy of the photon is h nu. So the photon or quanta is completely transferring its energy to the electron, right? So the right hand side of the equation must be equivalent to the left hand side of the equation, and h nu naught is less than h nu. Otherwise the electron would never come out. That's pretty simple to understand. But what is half MeV square? You have learned in class 10 the concept of kinetic energy. Just like I have potential energy when I jump up, there is a kinetic energy of a moving particle. These sorts of energies are called mechanical energies. I'm pretty sure you know this by now. So when an electron actually leaves the potassium metal, it possesses kinetic energy, and that's where the extra energy goes. So h nu naught was the minimum energy plus the kinetic energy. That's equivalent to the total energy, which is h nu, which is the energy of the photon. That's all you need to know when we talk about this part. Also h nu, so nu is equal to c by lambda, because we just learned c is equal to nu lambda. So E is equal to hc by lambda. This is one formula which you must remember. The last thing I'll be talking about on this board is the concept of 1 mole. Now because an atom is very small, in a very small volume you can actually have trillions, in fact 10 to the power 23 atoms. 10 to the power 23 is a huge number. So just like 1 dozen is equal to 12, 1 century is equal to 100, 1 mole is equal to 6.022 into 10 to the power 23. And we generally use it for molecules and atoms because this number is very huge and they are very small. So this question is very important from the examination point of view. On a scale of 1 to 10, I would rank this a 8. Listen very carefully, I'm pretty sure you get it because it is just based on the previous concept we have just learned. Now, they say there is a light with a wavelength of 300 nanometers. 1 nanometer is 10 to the power minus 11 meters, hence 300 nanometers is 3 into 10 to the power minus 9 meters. They say that it is projected on potassium metal and 1 mole electrons are being released. So 1 mole is 6.022 into 10 to the power 23. So the kinetic energy of all those electrons is 1.68 into 10 to the power 5 joules per mole. What you have to do is find the minimum energy required to remove 1 electron. This question might seem very heavy, but it is actually pretty easy. We have just learned the formula E is equal to h nu, which is equal to half MeV square plus h nu naught. Here h nu naught was the minimum energy to remove 1 electron, h nu was the energy of the photon, and half MeV square was the kinetic energy. So it's pretty clear that if we find h nu and we have already kinetic energies, we just subtract them, then we can easily get h nu naught, right? But the one thing is that the kinetic energy is given of 1 mole of electrons, not of 1 electron, right? So first, let's do the first step. We find energy of the light. Energy is equal to h nu, which is hc by lambda, because nu is equal to c is equal to nu lambda. Now energy is equal to h, which is 6.02 into 10 to the power minus 34, into c is always constant, 3 into 10 to the power 8, upon lambda, and lambda is given 3 into 10 to the power minus 9. Simple substitution. When we solve this, we get the value of the energy, right? But to remove 1 mole of electrons, 1 mole of photons is required, because 1 photon would remove 1 electron. Therefore, we multiply this number by 6.022 into 10 to the power 23, because this is the energy of 1 photon. We want to find the energy of 6.022 into 10 to the power 23 photons, because we know the kinetic energy of 1 mole. So we want to standardize everything. We could have divided this by 6.022 into 10 to the power 23 also, which would have made our answer shorter, but this is a bit easier to explain. So all we do is multiply this number by 6.022 into 10 to the power 23, because we need the value in 1 mole. So we get 3.99 into 10 to the power 5 joules per mole, and this is h nu. Okay. Now E is equal to h nu, which is half mev square plus h nu naught. We know this value, 1 mole of photons, the energy of 1 mole of photons. We know the value of 1 mole of kinetic energy of electrons. Simple subtraction, h nu minus a half mev square, which is 3.99 into 10 to the power 5 joules per mole minus 1.66 into 10 to the power 5 joules mole. When we simply subtract them, we get 2.31 into 10 to the power 5, which is the value of h nu naught. But this is the value of 1 mole of electrons, the minimum energy required for 1 mole of electrons. So all we do is divide it by 1 mole, because this is the value of 1 mole. So if you divide it by 1 mole, you will get the value of 1 electron, the energy required by 1 electron. So after division, we get 3.84 into 10 to the power minus 19 joules, which is the minimum energy required to remove 1 electron. A quick recap of this question so that you understand what I am trying to say. We know a formula E is equal to h nu, we know the formula C is equal to nu lambda, and we know a formula h nu is equal to half mev square plus h nu naught, right? We know 1 mole is 6.022 into 10 to the power 23. We know Planck's constant is 6.626 into 10 to the power minus 34. We know speed of light is 3 into 10 to the power 8. So you see, we are using all those concepts which you have learned in one question, and which is why I am making you do this question. If you did not understand it, then just rewatch it, and you will also be able to revise all the concepts we have just learned. So before we continue, let's just recap about the stuff we have learned, because when we study about the Neal-Bohr model of atom, you must be very clear about the stuff we have already learned. So the first thing we learned was the charge of an electron is minus 1.6 into 10 to the power minus 19 coulomb, and coulomb was the SI unit of charge. Proton's charge was the exact opposite but equal, plus 1.6 into 10 to the power minus 19 coulomb. The mass of an electron was 9.1 into 10 to the power minus 31 kilograms. The way we represent anything in the periodic table is we write the symbol instead of x, then the atomic number, atomic mass, and the charge. The first important equation we learned was C is equal to nu lambda. Here C was the speed of light, which is equal to 3 into 10 to the power 8 meters per second. Nu was the frequency of the wave, and lambda was the wavelength of the wave. And electromagnetic wave behaves just like a wave as well as a particle. Then we learned wave number is equal to 1 upon lambda. It's just a number, it does not have any physical meaning. We will be using this a lot when we talk about the Neal-Bohr model of atom. So you must know wave number is nothing else but just 1 upon lambda. E is equal to h nu. We used this in the photoelectric effect experiment where we projected some light on the potassium metal and the electrons started coming out. So we knew that the energy of a photon is equal to h into nu. We learned that E was directly proportional to nu when we started heating the rod, and it gave a lot of colors, right? And h is equal to 6.626 into 10 to the power minus 34 joules. This was the Planck's constant. And the final thing we learned was 1 mole is equal to 6.022 into 10 to the power 23. I want you to pause this video and write all of this down with your own hands, and write it till you can write all of them without looking at this video. Otherwise you will not understand what the Neal-Bohr model of atom really says. Neal-Bohr says all the protons and neutrons are in the center, and the electrons move around them in a fixed orbit. Now there is not just one fixed orbit in which these electrons can move, but in fact there are infinite orbits in which they can move, and the only difference between these orbits is that they have different radiuses and different energies. So the one which is the closest to the protons and neutrons will have the least energy and the least radius, and as we move away the energy increases. But then how will an electron, so originally then the electron would want to be in the least energy orbit, right? So the electron would originally, if there is only one electron in this entire system, it would want to be in the lowest energy level, which is n is equal to 1. But it can also move to a higher energy level provided we give it some energy. Now how will we give it some energy? Let's say we give some light to it. So light has photons, and photons energy is equal to h nu, right? So because of that photon, the electron will absorb the energy and move to a higher energy level. And the difference in the energy levels of the two orbits is equal to h nu, which was the energy of the photon. So E2 minus E1 is equal to h nu. We can just move h in the denominator, then frequency would become E2 minus E1 upon h. Now, you remember when I talked about Rutherford model of atom, I said that two charged particles, if they move around each other, then they must go inside the proton, because F is equal to Q1 Q2 upon R square, and the electron would start radiating energy and would fall inside the proton and neutron in 10 to the power minus 8 seconds. Then why are these electrons not falling inside the protons and neutrons? The concept is very simple. We have studied the concept of momentum in class 10th. Momentum is mass into velocity, and anything that has momentum has inertia. Whenever momentum is in a circle, then we call it angular momentum. What Niels Bohr says is if the angular momentum of the orbit is an integral multiple of h upon 2 pi. Now what is an integral multiple? 1 is an integer, 2 is an integer, 3 is an integer, 4 is an integer, just like that. If these numbers are a multiple of h upon 2 pi, h is the Planck's constant, 6.626 into 10 to the power minus 34, and pi is 22 by 7. Whenever it is an integral multiple, it will move in an orbit because of its inertia. That's all you need to know. Even if you don't understand this part, it's absolutely fine, because this is out of your syllabus and it is never asked in examinations. Now, the radius of any of this orbit is equal to n square into 52.9 picometers. Right? Just like we have meters, we have picometers, and n is the number of that shell. So the first shell is n is equal to 1, the second shell is n is equal to 2, then 3, then 4, then 5, then 6, then 7, and so on. We can go to any number we want, and the radius would just be n square into 52.9. So let's just take an example. What would be the radius of the fifth orbit? So 5 into 5 square is 25, and we just multiply it by 52.9. So 25 into 52.9, that's the radius of the fifth orbit. I'm pretty sure you understood this part completely. Now, whenever an electron goes from a higher energy orbit to a lower energy orbit, it has to release energy, because it is going from a higher energy one to a lower energy one. So where does the remainder of the energy go? It goes away in the form of an electromagnetic wave, a photon, a quanta. It just goes out, and the frequency is told by all of this. Now what is all of this? When an electron goes back to the first orbit from any of the orbits, so from the second, third, and so on, if it comes back to the first orbit, then we call this entire series Lyman series. And the light which is emitted has a very high frequency, and it is an ultraviolet ray. Okay? Now if it goes to the second one, then the light which is released due to the electron going back to the less excited state, that is called a Balmer series. So from 3, 4, 5, 6, if it goes back to 2, then it's Balmer. If it goes back to 3, then it's Paschen. If it goes back to 4, then there is Lyman, and so on. It's given in your book pretty clearly, but that's all you need to know. If it comes back to its base state, and its base state is 1, it is Lyman, then 2 it's Balmer, 3 is Paschen. That's all you need to know. Now, a very important concept. The energy of any of these orbits is equal to minus RH into 1 upon n square. Now what was n? This was n is equal to 1, n, 2, 3, 4. So just the number of the shell. So if we say what is the energy of the third shell, so we just say energy of the third shell, so instead of n I would write 3, energy of the third shell is minus RH bracket 1 upon 3 square. And what is RH? RH is 2.18 into 10 to the power minus 18, and this is called Rydberg's constant. Very important value, must remember this. Now, when we want to find the difference between two energy levels, all we need to do is for example between third and second. So what I would do is E3 minus E2, and then I would do minus RH 1 upon 3 square minus RH 1 upon 2 square. That's all I would do, right? And using that, we convert this into a wave number. Now that is a completely different derivation which I don't want to get into. All you need to know is this: whenever an electron moves from a higher energy orbit to a lower energy orbit, or from a lower energy orbit to the higher energy orbit, the wave frequency, the wave number is equal to 109677 bracket 1 upon n1 square minus 1 upon n2 square. That's all. I'm going to repeat this. Whenever an electron goes from a lower energy orbit to a higher energy orbit, or from a higher energy orbit to a lower energy orbit, the wave number of the light it emits is equivalent to 109677 bracket 1 upon n1 square minus 1 upon n2 square. Now, for example, it's going from the second orbit to any other orbit. Then we just learned that if it goes to the second orbit, then it's called Balmer series. So whenever you would see instead of n1, 2 is written, then you can easily say this is a Balmer series. And for example, it's instead of n1, 1 is written, then we have just learned that if it is in 1, then this is Lyman series. Therefore, it's pretty simple. This would become a Lyman series example. Now, using this, you can just find any difference in the any wave number. So if I want to find what is the wave number if an electron goes from the second orbit to the third orbit, I just use wave number is equal to 109677 1 upon 2 square minus 1 upon 3 square, because it's going to the third orbit, and when I will solve this, I'll get the answer. The thing we're going to learn now is very interesting, and it's interesting because it's very recent. It was found after the 1900s, and it is taught usually on a PhD level when you're out for quantum physics, but this is in our syllabus. So the first thing I'm going to tell you might shock you forever. Matter is not only matter, but it is also a wave. Just like we learned that an electromagnetic wave not only behaves like a wave but also acts as matter, the exact same way matter not only acts as matter but also as a wave. Now we'll take my own example. The equation is lambda, which is the wavelength I am leaving behind, is equal to h upon mv, and h is Planck's constant 6.626 into 10 to the minus 34. Now, the wavelength I would be leaving behind if I was running towards you at 10 meter per second would be 6.626 into 10 to the minus 34 upon 65, which is my mass, multiplied by the speed I have, which is 10 meters per second. So my wavelength, the one I am leaving behind, is 1 into 10 to the minus 36 joules second. This is so small that looking at it or detecting it is impossible. But if instead of me there was an electron, this wavelength would be a measurable number. Electron has a mass of 10 to the power minus 31, and it has a pretty high velocity. It can go up to 200,000 meters per second or even faster than that. So imagine the wavelength an electron would actually be leaving behind. And this equation is called de Broglie principle. The second equation is, you cannot know the position of an electron if you know the velocity of the electron. And if you know the position of the electron, you cannot know the velocity of the electron. This means that all model of atoms we have learned until now are completely wrong, because they say an electron is moving in a fixed path, which means you can predict where an electron would be at a particular point in time. But we just learned that you can either know the position or the velocity, you cannot know both of them. Hence, you can only know the probability, the region in which you can find the electron, but you will never be able to find the electron. The second thing this equation actually tells us is that an electron can be at more than one position at one point in time, because you cannot know the exact position. Now let's take a pen in our hands and move it really fast. So you would see it is at every position, but if you put your finger over here and it stops, then you know that it is at one position. But in case of electron, you know it is at every position, and when you put your finger, then you won't know what the velocity it has. What is the velocity that it has? So you can never know the exact next position it's going to be in. And hence we say an electron is actually at more than one position in time. Now this is really complicated, and I don't want you to get confused because of it. I just wanted to tell you because this is a very interesting scientific fact. And this is actually a scientific fact. Now what the equation says is that delta x multiplied by delta v is greater than equal to h upon 4 pi m. Delta x is the uncertainty in position, delta v is uncertainty in velocity, and it is always greater than equal to h upon 4 pi m. That's all you need to know. M is the mass, h is Planck's constant, 4 pi is a constant. Now, this equation is actually a PhD level equation. This is actually called the psi function. It has no physical meaning. Just the way wave number didn't have any physical meaning, this does not have any physical meaning. But the square of this number tells us the probability, the region in which the electron will be found. And hence psi square has a physical meaning. And it tells us, and it is called the probability function. So first let's understand what is an orbit and what is an orbital. An orbit is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. The model which Niels Bohr gave was not completely wrong. The radius he predicted for these orbits was absolutely perfect, 52.9 n square. And in one orbit, the maximum number of electrons that can be contained is given by the formula 2n square. So if I say what is the number of electrons that will be contained in the third orbit, then you can easily say 2 into 3 square, which is equal to 18. If I say what is the number of electrons in the second orbit, you will say 2 into 2 square, which is 8. If I say in the first orbit, then you would say 2 into 1, which is 2, right? So that's an orbit. Now what is an orbital? An orbital is a little complicated, so I need your full attention right now. Within n is equal to 1, there are 2 electrons, and one orbital can contain a maximum of 2 electrons. Hence, there will be one orbital in n is equal to 1. Now, what is an orbital? What does it look like? An orbital is a 3-dimensional shape which has the maximum probability of containing an electron. So, if the shape is a sphere, then there is a 99% probability that I would find the electron in that sphere. So n is equal to 1, imagine it to be a sphere, and 2 electrons has the maximum probability of being in that sphere. They can be the other end of the galaxy for all we know, but the 99% probability is that they will be found within this sphere when we talk about n is equal to 1. Now when I say n is equal to 2, you remember we used the formula 2n square, and we came to a conclusion that there will be 8 electrons, and one orbital can contain a maximum of 2, therefore there will be 4 orbitals. That's a simple division. So there would be a 1s over in n is equal to 1 and a 2s in n is equal to 2. A 2s would be a sphere but would be a bigger sphere, which would be equivalent to the radius of n is equal to 2. So that would be the first kind of orbital. The second kind of orbital would be looking like a 8. It's called the p orbital. The p orbital can be in 3 orientations. This can be on the x-axis, this can be on the y-axis, and this can be on the z-axis. So you see 3 orientations. And therefore we say px, py, and pz. They are the 3 orientations of p. And again, one orbital can contain a maximum of 2 electrons. So 1s would have 1s orbital, n is equal to 2 would have 1 2s orbital and 3 p orbitals. So it would have 1 2s, 1 px, 1 py, and 1 pz, which would make a total of 8 electrons, right? Now what are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum numbers? Principal quantum number tells us about the size of the main orbit, right? Azimuthal quantum number tells us about the shape of the orbital. Magnetic quantum number tells us about the orientation of the orbital. So if I say px, py, and pz, I'm talking about the orientation that the p orbital is in. That is what the magnetic quantum number tells us. And the spin quantum number tells us that the 2 electrons which are present within that orbital, what is the direction of the spin. So whether it is moving clockwise or anti-clockwise. That is all about the quantum mechanical model of the atom. Now we are going to be talking about some last few concepts of this chapter. The first one is Pauli's exclusion principle. It says that no 2 electrons can have the exact same set of 4 quantum numbers. So if the principal quantum number is same, for example the second orbit, then the azimuthal quantum number and the magnetic quantum number are same, for example px, both of them are in px, then the spin quantum number must be different. If one is moving in clockwise direction, then the other one must be moving in anti-clockwise direction, and hence in one atom any two electrons would have 4 different quantum numbers. That's all you need to know about Pauli's exclusion principle. Now this Aufbau principle is very important. What it says is this: the subshell with the lowest energy will get filled first. So 1s would definitely have the lowest energy, P has the second lowest energy, D had the third lowest energy, then comes F, and we can go on. There is no limit to the number of subshells we have, but we will only be talking till F. So 1s would be the first one to be filled. Then there would be 2s. We just follow these arrows. Then there comes 2s, then there comes 2p, then there comes 3s. So 2 electrons get filled here, 2 electrons get filled here, 6 electrons get filled here, 2 electrons get filled here. Then we go to 3p, 6 electrons get filled in 3p. In 4s, 2 electrons get filled. And then we go to 3d. In 3d, we fill 10 electrons. Then we go to 4p. And then we go to 5s. Everything is going normal until now. But then you would see after 5s I am filling 4d. While ideally you would expect that we fill 4s, then we fill 4p, and then we fill 4d. But because 4d has an exceptionally high energy level, that is why we are filling 4d after 5s. So we are first going to the 5th orbit, filling the s, and then coming back to the d orbit of the 4th. Then we fill 5p, then 6s, then we fill 4f. So you realize how high energy level 4f has, that we are first filling the 6th orbit and then going back to the 4th f1. So this is you just have to follow these arrows. You don't have to remember all of this, but it would be great if you could learn how to draw this diagram, and I'll be putting the link in the description. In short, if I were to explain how to make this diagram, I just make horizontal lines, and in the middle of those horizontal lines I make one more line. So 1s, and then I go back down. In the middle I draw one more line, then I go back up, down, then in the middle I draw one more line, and I keep doing this till I reach the end. So that was all about it. In examinations they would ask you to make some the electron configuration for chlorine. So you probably just have to remember the stuff till this point, till 4s, which is pretty easy to remember, so you won't have to make the diagram again and again. Now, S has 2 electrons, P has 6, D has 10, and F has 14. Why do I say this? S is a subshell, and one subshell can have as many orbitals as it wants, right? But it depends on the orientation. So S can only have one orientation because it is a sphere. We discussed P can have 3 orientations. So Px, Py, and Pz. In total there are 6 electrons because one orbital can have 2 electrons. D has 5 orbitals. Hence the total number of electrons are 10. F has 7 orbitals because of the different orientations. So the total number of electrons are 14. Now if I were asked to make the electron configuration for chlorine, what would I do? First I would follow this. So I know chlorine has 17 electrons, so I need to fill 17 electrons. That means first I'll fill 1s, so that's 2, then 2s, so that's 4 electrons in total, then there is 2p, so 4 plus 6, that's 10, then there is 3s, which is 2 more electrons, so that's 12, and in 3p there should be 6, but I have to fill 5 electrons, so I also take 3p. So I take this entire thing and I write it over here. Fine. Now I write 1s2 because 2 electrons are being filled, then I write 2s2, then I write 2p6, then I write 3s2, and then I write 3p5. Now why do I write 3p5? I had 17 electrons. Till 3s2 I have filled 12 of them, which means I have 5 remaining. Hence in 3p I cannot fill the 6th empty part, and hence I write 3p5. Otherwise I would have written 3p6. It's as that easy as that. Now I have written K, L, and M over here. When n is equal to 1, we call that orbit K. When n is equal to 2, we call that orbit L. When n is equal to 3, we call it M. And then N, O, P, Q, R, S, T, U, W, X, Y, Z, as we keep going down the orbits. So when I say 1s, then I write K. All the 2 come in L. All the 3 come in M. Now if I were to write the electrons, I want to explain the clockwise and anti-clockwise nature in the electron configuration. This is the kind of diagram I would be drawing. First I would obviously write 1s, 2. So I fill 1 in the clockwise and 1 in the anti-clockwise. Then 2s2, 1 in the clockwise, 1 in the anti-clockwise. Then when I enter the P, first I fill Px, so I would have 1 in clockwise, then I would fill 2 Py, then 1 in clockwise, and then Pz, 1 in clockwise. And then I would fill the anti-clockwise. So then I would go back to 2Px, fill the anti-clockwise, then go to 2Py and fill the anti-clockwise, and then go to the 2Pz and fill the anti-clockwise. Similarly, we fill 3s2, and in 3p5, clockwise, 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 anti-clockwise, anti-clockwise, and we run out of electrons. Hence, this part is empty. So this is the way you are expected to write the electron configuration. That's all you need to know for this chapter. Thank you so much for watching. I hope that you understood everything. Even if you didn't, you can email me anytime at my email address, which is down in the description. It is nakul@swapapp.co. And if you have any doubt, just rewatch the video. I'm pretty sure this video will be enough to explain everything. I hope I will see you in the next video. See you then.